So now I'm going to give a second graphical interpretation of what our double integrals look like. And this will help set up one of the techniques of integration that we're going to need, which is Fubini's theorem of being able to interchange the order of integration. So let's think of this sheet up here as my function, f of xy. And here I have my rectangular region. In this case, the rectangular region is given by the interval AB along the x-axis, crossed with the interval CD along the y-axis, as I have this labeled. And again, for our double integration, we're going to be thinking about finding the volume of this region that has this rectangular base and a height that is given by the curvy top of this function. So this is like some curvy top of the function, right? It follows the functional values. Oops. Maybe I should have done that in a different color. That's okay. I'll add a color now. So one way that we can think about computing what's going on with this integration is I can think about setting x equal to a constant. So let's think about if I were to set x equal to some x naught and slice a thin slice out of the volume of this region. What happens? I'm setting x equal to a constant. I'm going to slice. It's going to be a vertical trace where x is equal to some constant. And I end up with this cutout of a region. So I'm just thinking of what is the area of the cutout of this region here. So this is where my x is constant, my y's are going from c to d, and the heights along here are going to be the heights of this function where x is held equal to a constant. So the area of the blue slice is given by an integral. And it's the integral where my y values are varying. My y values are going from c to d. But in this case, my x values are fixed constant at x naught. So it's an integral only of one variable. And it's an integral evaluated at f of x naught comma y dy. So this is the area of the blue slice. And if I were to think about computing the entire volume just by summing up a whole bunch of these blue slices, instead of just looking at the slice at x naught, I would want to look at all of the slices. And I would have to add up the areas of all of the slices as x's go from a to b. And for each of those slices, the widths of each of these slices can be thought of, obviously these are infinitesimals. My width in this case, maybe I'll write this here, could be thought of as my change in x, which when I take the limit ends up being, this is supposed to be the width, ends up being my differential dx. So if I sum up all of the slices in this direction, I would have to be integrating as my x naught values went from a to b, and the width of each, maybe I'll write this in black, that'll be clearer. Integral as my x value goes from a to b, and the width of each of those slices is given by dx. So notice this is exactly the formula that we had before. Now, because our x values are changing, I no longer have that constant x value. And this is the area of the blue slice, but then the black parts say that I'm going to sum over all slices. So my interior integral is giving me the slice where my x naught is held constant, and the exterior integral is telling me I want to add up all of those slices of bread. If I think of this as a loaf of bread, I need all of those slices of bread as my x goes from a to b. Similarly, instead of thinking of the slice in the x direction, or holding x constant, I can do the exact same thing, only this time I'm going to hold my y value constant. So I'm going to erase some of these pieces. Hopefully it'll still be an intelligible diagram. So before we held x naught constant, now I'm going to think about holding y naught constant. Oh, I guess I need a, there we go. So let's fix y at some place. and I'm going to cut out a slice of bread in this direction. So this time, instead of slicing my loaf of bread with X slices, I'm going to slice my loaf of bread with a bunch of Y slices. And similarly, if I wanted to know the area of the red slice, it's exactly analogous. In this case, we're holding our y naught constant, so I'm going to think of this as a function of x, where y naught is held constant. And my x's are going to be changing from x equals a to x equals b. So here my x is going from a to b dx, because really it's just this flat area. We know how to find integrals where we're looking at areas. That's exactly our integration technique from a single variable. But then I want to sum over all of the slices. And so I'm going to sum in the y direction as my slices go through every single slice of bread, as I go from y equals c all the way to where y equals d, dy. So what this is telling us, dun, da, 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 all of this visual graphical interpretation, obviously this isn't a formal analysis proof, but we don't need formal analysis proofs, is that we're saying that if I take the area of the blue slice and sum all of the slices, that's going to give me the same thing as the area of the red slice and summing up all of the slices. And the grand conclusion is what we call Fubini's theorem. So what does Fubini's theorem tell us? Fubini's theorem tells us that if I have a rectangular region where my x's are going from a to b and my y's are going from c to d, then the integral with y on the outside as y goes from c to d, and then with x on the inside as x goes from a to b, is going to be exactly equal to the integral where I take the x on the exterior of the double integral, where my x's go from a to b and my y's go from c to d. There are two things that I want you to note here. That it's always the case that my y values are traveling exactly the y coordinates of the rectangular region. It's not that I'm flipping my x and y intervals. So my y's are always going from c to d, and my x's are always going from a to b. This may seem like a trivial point, but when you're caught up in calculations, that's important to remember. And then the second thing that's important to remember is that if the x's are in the interior of the integral, that's what I need to integrate first. And if the y's are in the interior of the integral, that's what I would need to integrate first. So this is a Fubini's theorem. We're now going to do a number of examples where we actually put this theory into practice and compute some double integrals.